Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, Delhi, India. Today we are going to discuss about the module Auger Electron Spectroscopy Part 1. This is under the chapter Spectroscopic Methods from the paper Characterization Techniques for Materials 2. From this module, students may get to know about the following. We will introduce the Auger electron spectroscopy, the basic principle and instrumentation of the Auger electron spectroscopy will be discussed. The qualitative analysis of the Auger electron spectroscopy will also be discussed. The Auger electron spectroscopy, generally termed as AES, is an analytical, non-destructive and efficient technique used to determine the elemental composition of the surface layers of a solid material. The secondary electrons emitted due to Auger process are analyzed and their kinetic energy is determined. Each element in a specimen would produce characteristic spectrum of peaks. The Auger effect was discovered independently by both Lise Meitner and P. Auger in the 1920s. Auger electrons are emitted at discrete energies and help to identify the origin of the element. The idea of using stimulated Auger signals for surface analysis was first suggested in 1953 by J. Lande. The technique became practical for surface analysis after Larry Harrison in 1967 demonstrated the use of differentiation to enhance the Auger signals. Auger recognized that an atom in the excited state could return to the equilibrium state by releasing energy through ejection of an electron from the upper level. These electrons have characteristic energies depending on the electronic structure of the element, and hence the characteristic energies could uniquely identify the element from which the electron is ejected. The first commercial Auger electron spectrometer became available in 1969. This is becoming one of the most popular methods of surface analysis. AES is very powerful surface analytical technique that has found applications in many fields of solid state physics and chemistry. It is a surface specific technique utilizing the emission of low energy electron in the Auger process and is one of the best common employed surface analytical techniques for determining the composition of the surface layers of a sample. Let us study the principle of Auger electron spectroscopy. Figure 1 illustrates the emission process of an Auger electron when a high energy electron strikes an atom with energy of the incident particle high enough to knock out the inner shell, generally termed as K shell, electron of the atom, shifting the atom to ionize and the atom belongs to the excited state. The atom will quickly return to its normal state after refilling the inner electron vacancy with an outer shell electron. During this transition process, the energy difference between the outer and inner shell electrons may cause emission of either a characteristic X-ray photon by radiating through a radiative process or Auger electron from an electron shell through non-radiative process. Auger is a radiationless process where an excited ion decays into two doubly charged ions by ejecting an electron. The kinetic energy of an Auger electron is approximately equal to the energy difference between the binding energies in the electron shells involved in the Auger process. For example, the kinetic energy of an Auger electron in figure 1 is approximated by the following equation: E k L1 L2 is equal to E of Bk minus EBL1 minus EBL23. The notation for kinetic energy of Auger electron describes its origin, but the nomenclature is rather complicated. For example, the kinetic energy of an Auger electron in equation 1 is from a process illustrated, that is, an incident electron knocks out a K shell electron, a L1 shell electron refills the K shell vacancy, and a L23 shell electron is ejected as the Auger electron. The subscript of EBX indicates the binding energy of electron shell X. For example, EBK is the binding energy of the K shell. Auger electron spectroscopy identifies the elements by measuring the kinetic energies of the Auger electrons. In the spectrum, an individual kinetic energy peak from an Auger electron is marked with an elemental symbol and subscripts indicating the electron shells or subshells involved. The instrumentation. A modern instrument for electron spectrometry contains both the XPS and AES in a single chamber as a multifunctional surface analysis system. A scanning electron microscope or the SEM system may also be included in order to image the microscopic area to be examined by electron spectroscopy. Figure 2 schematically illustrates the block diagram of Auger electron spectroscopy and XPS, including an electron gun, an X-ray gun, and a shade analyzer of electron energy. The electron beam for generating the Auger electron emission is focused and scanned over a sample surface to obtain two-dimensional mapping for AES analysis. The AES analysis is commonly used in scanning type called scanning Auger microscopy. The main components of AES are ultra high vacuum system, source guns, electron energy analyzer. First, let us study about the ultra high vacuum systems. The ultra high vacuum is required to reduce the chances of low energy electrons being scattered by gas molecules on their way to reach at the detector, and to keep the sample's surface free from contamination from the gas molecules. Low energy photoelectrons and auger electrons are easily scattered by the gas molecules. Scattering reduces the signal intensity and increases background noise in the spectra. The ultra-high vacuum chamber is commonly prepared using stainless steel, and joints of chamber parts are made from crossed copper gaskets. Ultra-high vacuum can be achieved using diffusion pumps, sputter ion pumps, or turbomolecular pumps. Magnetic shielding is also required for chamber to change the trajectory of signal electrons, since the electrons are affected by the magnetic field. Second is the source guns. It contains X-ray guns, electron guns, and ion gun. First, the X-ray gun. An electron spectrometer system contains an X-ray gun for XPS analysis. The X-ray gun produces a characteristic X-ray line to excite atoms of the surface to be analyzed. The XPS uses monochromatic and non-monochromatic X-ray sources. The output from a non-monochromatic X-ray source consists of continuous energy distribution with high intensity of K alpha characteristic lines. The monochromatic source produces output by removing continuous X-rays from a radiation spectrum. The energies of aluminum K alpha and magnesium K alpha are 1.4866 and 1.2536 kiloelectron volt respectively, which is lower than energies of copper K alpha, which is equal to 8.04 kiloelectron volt, and molybdenum K alpha is equal to 17.44 kiloelectron volt. These are commonly used in X-rays diffractometry. The reason to choose lower width of X-rays is their narrow line width. The line width of characteristics X-rays refers to their range of energy. XPS requires a line width less than 1.0 electron volt to ensure good energy resolution. Both aluminum K alpha and magnesium K alpha exhibit line widths less than 1.0 electron volt and also have sufficient energies for photoelectron excitations. Now, the electron gun. The electron gun used in AES analysis is similar to those used in electron microscopy. Lanthanum hexaboride, termed as LaB6, and field emission guns are commonly used in electron spectrometers. Lanthanum hexaboride provides an electron beam of high brightness with spatial resolution of 200 nanometer. Field emission guns provides superior brightness and higher spatial resolution than lanthanum hexaboride, and also their emitting surface remains clean during operation without adsorption of gas molecules. Then ion gun. The function of ion gun is twofold in XPS. Firstly, it provides high energy ion flux to clean sample surfaces before examination. Sample surfaces are commonly contaminated with adsorbed hydrocarbons, water vapors, and oxides that need to be removed before surface analysis. The second function is to sputter out sample atom layer by layer so that an elemental depth profile can be revealed. The ion gun produces an argon ion beam by either electron impact or gaseous discharge. Electron energy analyzers. An Auger electron spectroscopy. The spectrum is recorded using an electron energy analyzer as shown in figures 3. The most commonly used analyzer is the concentric hemispherical analyzer, termed as CHA, also called hemispherical sector analyzer, which is HSA. The analyzer is composed of two concentric hemispheres with radii R1 and R2, and its working principle can be understood from the figure. Negative potentials V1 and V2 are applied to inner and outer hemispheres respectively. The applied potential generates a median equipotential surface with radius R0. The potential along the median surface V0 is called the pass energy of the CHA. A slit at one end of the CHA allows electrons from the sample to enter, and a slit at the other end of the CHA lets electrons pass through to an electron detector. Auger analysis requires suppressing the electron signal at the low energy end of the spectrum. The CRR mode meets the Auger analysis requirement because the CHA mode exhibits a low transmission rate with low pass energy. When a constant retardation ratio is applied, a low Auger electron energy generates low CHA pass energy. For example, with a retardation ratio of 10, the pass energy is only 10 electron volt for E is equal to 100 electron volt, and the pass energy is 100 electron volt for E is equal to 1000 electron volt. In other words, electron transmission through a CHA is lower at a pass energy of 10 electron volt than at 100 electron volt. An Auger spectrum is commonly recorded by changing the CHA pass energy in the CRR mode. The AES spectra. A typical AES spectrum is a plot of intensity versus kinetic energy. It is a plot of the first derivative of intensity versus the kinetic energy. The Auger peaks appear small against the background of the direct mode spectrum. This occurs because the signals from Auger electrons are relatively weak compared to the secondary electrons escaped from a solid surface. Electrons are either elastically or inelastically scattered when a primary beam strikes the material. Auger spectra can be expressed in two modes, a direct mode and differential mode as shown in figure 4. The direct mode presents the intensity distribution in a range of electron kinetic energies. The differential mode presents the derivative of intensity versus the kinetic energy. The differential mode is more widely used because the Auger peaks are more obvious than in the direct mode. Figure 5 shows the Auger spectra of palladium metal as an example. The CRR mode of the CHA generates a constant relative resolution delta E divided by E over the whole range of the spectrum. The direct mode spectrum required with CRR mode expresses the energy distribution as the number of electrons multiplied by its kinetic energy E times Ne as shown in figure 5a. The differential mode spectrum is produced by taking the first derivative of the curve in the direct mode using computer software. The ordinate should be E dn, which is a function of E. In the differential mode spectrum with CRR acquisition is shown in figure 5b. The differential mode effectively reduces the background and enhances the Auger peaks. Let us see what are the applications of AES. Auger electron spectroscopy is used to monitor the elemental composition of surfaces during physical property measurements. Several phenomena such as adsorption, desorption, surface segregation from the bulk, measurement of diffusion coefficient and catalytic activity of surfaces can be investigated. It is used to study the compositional changes on the surface of alloys during ion sputtering. Generally, the chemical properties including corrosion, stress corrosion, oxidation and catalytic activity and mechanical properties such as fatigue, wear, adhesion, resistance to deformation processes and surface cracking depend on surface properties. The grain boundary chemistry influences mechanical properties such as low and high temperature ductility and fatigue. Chemical properties such as intergranular corrosion and stress corrosion and electrical properties. AES has been used to relate surface and grain boundary chemistry to properties of material. AES has proved to be extremely valuable compared to most other techniques which are limited by either large sampling depth or poor sensitivity. So students, let us summarize what we have learned in this module. Auger electron spectroscopy is an analytical and non-destructive technique and used to determine the elemental composition of the surface layer of the solid material. The basic principle of AES is Auger effect, and Auger is a radiationless process where an excited ion decay an excited ion into two doubly charged ions by ejecting an electron. The block diagram of AES includes an electron gun, an X-ray gun, and a SED analyzer of electron energy. The electron beam for generating the Auger electron emission is focused and scanned over a sample surface to obtain two-dimensional mapping for AES analysis. A typical AES spectrum is a plot of intensity versus kinetic energy. It is a plot of the first derivative of intensity versus the kinetic energy. The Auger peaks appear small against the background of the direct mode spectrum. Thank you.